Look, I'm 85 years old. I've been doing theoretical physics for over 60 years. And so I've started fights with Nobel laureates. I've been called a crackpot more than once. And I've outlived some of the smartest people who ever walked this planet. So when I tell you that the most exciting time to be a physicist is right now in 2026, I want you to understand that I'm not just saying that. I've lived through the string theory revolution. And so I watched the holographic principle go from a crazy idea to the foundation of modern physics. I was there for the black hole wars. And so I'm telling you what's coming next makes all of that look like a warm-up act. It's the questions we're circling right now about quantum gravity, about what our universe actually is, about whether de Sitter space can even have a quantum mechanical description. These are the deepest questions in the history of science, and we are close. Maybe not close enough for my taste given my age, but close. Let me tell you what I see. People ask me sometimes, journalists, students, my wife, Lenny, what's it like looking back on 60 years of physics? And honestly, it feels like one long connected thread. And so I didn't plan it that way. When I was a kid in the South Bronx, my father, he was a plumber, he told me, you ain't gonna be no engineer. You're going to be Einstein. He meant it as a joke, I think. Maybe not. But when I started doing physics, I wasn't thinking about my legacy or my research program. I was just trying to understand things that didn't make sense. And here's the honest truth. Almost everything I've worked on in my career started because something didn't add up. String theory in 1970. I was sitting in my office. I'd been looking at this formula by Veneziano, and I suddenly saw that it was describing a string vibrating, not a point particle. Nobody else had seen it that way. I didn't sit down that morning planning to co-discover string theory. I was just confused. And then for about 30 seconds, I wasn't confused anymore. And then I was more confused for the next 50 years. That's physics. You solve one mystery and 3 more open up behind it. It's the black hole information paradox that occupied the central part of my intellectual life from about 1981 until Stephen Hawking finally conceded the argument in 2004, 23 years. And even then, it wasn't really over. We'd won the battle, but not the war. The deep questions were still there. It's the landscape of string theory, the idea that there are something like 10 to the 500 possible universes, and we just happen to be in one that supports life. That one, I'm still fighting. It's for Lee Smolin thinks I've gone off the deep end. I think Lee hasn't thought about it hard enough. And then for the last decade or so, it's been quantum complexity, de Sitter space. It's the question of what happens to quantum gravity in a universe like ours, which is accelerating, expanding, a universe that has a cosmological constant and therefore a cosmological horizon. It's 60 years and the thread is continuous. Every idea connects to every other idea. That's the thing I want to tell you today. In 2026, I'm not doing something different from what I was doing in 1970. And so I'm doing the same thing at a deeper level with better tools. So let me take you through what I think the most important open questions are. And I'll tell you honestly, this is one old man's opinion, but this old man has been thinking about this stuff longer than most of you have been alive. Here's the situation as I see it. So we have 2 great theories of physics, quantum mechanics and general relativity. Quantum mechanics describes how particles and fields behave at tiny scales, atoms, electrons, photons, the fundamental bits of matter. General relativity describes how space and time curve in the presence of mass and energy. It's Einstein's great theory of gravity. Both theories are extraordinarily successful. Both of them work with incredible precision in their respective domains, and they cannot both be completely right. Not in the sense that either of them is wrong, exactly. They're both right in the regime where they've been tested, but they're fundamentally incompatible. They're based on different mathematical structures, different assumptions about how the world works. And when you push either of them to extremes, when you ask what happens at the center of a black hole, or at the Big Bang, or at the Planck scale, where quantum effects and gravitational effects are. It's both important. They break down, they give you nonsense, infinities, contradictions. It's the great project of theoretical physics, really since the 1930s, but with real urgency since the 1970s, is to find the theory that unifies them, the theory of quantum gravity. Now, I spent 40 years working on string theory as the candidate for that unification, and I still think string theory is the most powerful set of tools we have for thinking about quantum gravity. It's the consistency of string theory, the way it naturally incorporates gravity, the way it's connected holography and black hole physics and quantum information. It's an extraordinarily rich structure. But here's something I'll admit that younger physicists sometimes won't. We don't yet understand string theory deeply enough to call it a finished theory. And so we don't even know exactly what string theory is. We have a collection of different looking theories that we think are all facets of the same thing, the thing we call M theory, but we don't have a complete, non-perturbative, fully unified formulation. That's problem number one. Problem number two is even harder, and it's the one that's keeping me up at night. It's almost all of our understanding of quantum gravity, the holographic principle, ADS-CFT, the connection between entanglement and geometry that Juan Maldacena and I called ER-EPR. It comes from studying physics in what's called anti-de Sitter space, ADS space. This is a universe with a negative cosmological constant, and it has a very particular geometric structure that makes it amenable to holographic analysis. So you can put the whole 3D universe on a 2D boundary, and the two descriptions are exactly equivalent. It's beautiful. Juan's AD-CFT correspondence, which he discovered in 1997, is probably the most important theoretical discovery in physics in the last 30 years. But here's the problem. We don't live in anti-de Sitter space, we live in de Sitter space. Our universe has a positive cosmological constant. It's not curving inward, it's expanding, accelerating, and that expansion is getting faster, and de Sitter space behaves completely differently from anti-de Sitter space. In ADs, you can have a boundary at infinity that the information never crosses. In de Sitter space, you have a horizon, a cosmological horizon, and information disappears behind it, just like it disappears behind a black hole horizon. So you can't even see most of your own universe, and nobody knows how to do holography in de Sitter space. We don't know what the theory on the boundary is. So we're not even sure there is a consistent quantum mechanical description of de Sitter space. That's not a technical gap. That might be a fundamental problem with our entire conceptual framework. So I called a paper I wrote in 2021, 3 Impossible Theories. Not because the theories are impossible in some philosophical sense, but because every approach to quantum gravity in de Sitter space runs into what look like fundamental, irresolvable contradictions. And that is a very strange situation to be in. It means we're missing something deep, something conceptual, and something that's going to require a real revolution to understand. That's problem number 2. And in my view, it's the central open question in fundamental physics. Problem number 3 is experimental. One of the critiques that Lee Smolin and others have made of string theory and of quantum gravity research more broadly is that it's disconnected from experiment. We can't test these ideas. And you know what? That critique has some merit. I don't love hearing it, but it has merit. The Planck scale, where quantum gravity effects are important, is so far beyond what any particle accelerator could probe that it's almost laughable to think about reaching it directly. The gap between the highest energy we can probe experimentally and the Planck energy is roughly 15 orders of magnitude. That's a factor of 1,000,000 billion. It's not happening anytime soon. So what do we do? How do we make progress when experiments are seemingly out of reach? This is actually one of the most exciting developments of the last 10 years. And it connects to something that I wouldn't have predicted even 20 years ago, quantum computers. Let me tell you about something that changed my thinking significantly. A few years ago, Adam Brown and I, along with a big group of collaborators, published a paper in Nature showing that you could simulate wormhole-like dynamics on a quantum computer. We called it a holographic wormhole in a quantum computer. Now, I want to be careful here because this got sensationalized in the press. We did not create an actual wormhole. We're not that good. And what we showed is that the mathematical structure underlying wormhole physics, the information theoretic dynamics, the scrambling, the teleportation through the wormhole, you can simulate all of that on a quantum chip. The quantum computer was running a version of something called the SYK model, the Sachdev-Yeh-Kitev model, a quantum system of interacting fermions that has deep connections to black hole physics. Here's why I think that's significant, and not just as a party trick for most of my career. Quantum gravity lived in a purely theoretical world. So you'd work on a paper for 3 years, derive some result, and then there was nothing you could do to check it against reality. You checked it against other theoretical results. It's against consistency arguments, against mathematical elegance. That's not nothing, but it's not the same as experiment. What quantum computers open up is the possibility of actually running quantum gravity systems and watching what happens, not at the Planck scale, but in a regime where the same mathematical structure is present. This is like, imagine you couldn't test fluid dynamics by building a real airplane, but you could simulate the Navier-Stokes equations on a computer and watch the airflow. It's not the same as flying, but it tells you real things. In 2023, our group published Quantum Gravity in the Lab, actually 2 papers, proposing specific protocols for testing quantum gravity concepts using quantum computers. Teleportation by size. Traversable wormholes, these are real experimental proposals. There are labs working on implementing them right now. I think this is the beginning of a new era in quantum gravity research. It's the era where theory and experiment, or at least theory and simulation, start talking to each other again. Now, let me tell you what I think the biggest conceptual breakthrough needed is. This is my current obsession, and I'll warn you, it's speculative. This is frontier stuff. I'm not telling you what we know, I'm telling you what I think. And so I think the key to everything is understanding the relationship between computational complexity, geometry, and time. Okay, so here's the idea. Starting around 2014, I started thinking about the firewall paradox. This problem that had been raised by a group called AMPS through a completely different lens. It's the lens of computational complexity. And what I found was that the question, does a firewall form at the horizon of a black hole, is actually equivalent to the question, how computationally hard is it to decode the Hawking radiation that's coming out of the black hole? And the answer is, it's exponentially hard. Specifically, it's hard in a way that corresponds to a specific geometric quantity, the volume of the interior of the black hole. The more the black hole has evaporated, the more complex the Hawking radiation has become, and the more complex it is, the bigger the interior of the black hole is. Here's the punchline. The interior of a black hole grows even after the black hole has stopped evaporating and reached equilibrium. It's the exterior, the size, the temperature, all of that reaches a steady state, but the interior keeps growing for an exponentially long time. And this growth is tracked by the quantum complexity of the black hole's quantum state. And in 2016, with Adam Brown, Daniel Roberts, and Brian Swingle, we published Complexity Equals Action. The conjecture was this: the quantum complexity of the holographic state is equal to the classical action of a particular region of space-time called the Wheeler-DeWitt patch. Complexity on the quantum side equals action on the classical gravity side. Now, that's a technical statement. Let me tell you what it means in plain language. In classical physics, Newton's mechanics, every system evolves to minimize something called the action. It's a number that captures the history of the system's motion, and nature always takes the path of least action. This is one of the deepest principles in all of physics. It's behind every equation, from Newtonian mechanics to electromagnetism to general relativity. What we found is that quantum complexity, a measure of how hard it is computationally to prepare a quantum state, is the quantum gravity analog of classical action. Black holes are, in a precise technical sense, maximally complex systems. They've reached a state where the complexity is as high as it can possibly be for their size. And they got there by being the fastest possible computers in nature. Think about what that means. A black hole isn't just a gravitational object, it's a computation. It's processing information at the maximum possible rate allowed by the laws of physics. And the geometry of the black hole's interior, the size of the wormhole, if you want to think of it that way, is literally encoding the progress of that computation. Time and complexity are connected, geometry and computation are connected. This is not a metaphor, it's a mathematical identity. Now, here's where I think this is all going, and this is my prediction for the future. Not established facts. I think that the theory of quantum gravity in de Sitter space, the theory of quantum gravity in a universe like ours, is going to turn out to be a theory of computation. It's not in some vague, hand-wavy sense, in a precise mathematical sense. It's the cosmological evolution of our universe, the growth of complexity, the appearance of space-time geometry. I suspect all of this emerges from some underlying quantum information theoretic structure. We've been chasing the idea that space and time are fundamental. that they're the stage on which physics plays out. I've come to believe they're not fundamental, they're emergent. They appear from something more basic, and that more basic thing has to do with quantum entanglement and quantum complexity. Gerard Hooft and I developed the holographic principle in the early 90s because we were convinced that space itself was encoding too much information, that a three-dimensional volume couldn't hold as much information as ordinary physics would suggest. The resolution was that the relevant information lives on the two-dimensional boundary. Space got reduced by one dimension. And so I think the next step is going to be even more radical. I think time is going to get reduced too. It's the unfolding of time, the directionality of time, the arrow of time. I suspect this is going to turn out to be computational complexity increasing. That's all the arrow of time is, complexity going up. If that's right, then the laws of physics at the deepest level aren't about space and time at all. They're about information and complexity and entanglement and all the rest. All the geometry, all the curvature, all the particles and fields is the emergent consequence. I want to be honest with you about the state of these debates. Not everything I've just told you is accepted by the community. Some of it is controversial. It's the de Sitter problem, the question of whether quantum gravity even makes sense in de Sitter space, has generated some genuinely heated arguments. So I published 3 impossible theories in 2021. And the response from some quarters was essentially, sure, it's hard, but you're being too pessimistic. And from others, it is impossible, and therefore, string theory has failed. Neither of those reactions is quite right, in my view. And then there's a more specific ongoing debate about how to extend the kinds of holographic dualities we understand in ADS to de Sitter space. There's an approach developed by Narovlansky and Verlinde that I think is on the right track in some ways, but makes assumptions I disagree with about the boundary entropy and its relationship to this horizon area. My collaborator, Adil Rahman, and I have been going back and forth on this. We published comments on Narovlansky and Verlinde in 2023, and we've been updating it as the debate continues. It's an ongoing scientific conversation, and those are the best kind. But I want to talk about the bigger controversy. It's the one that's been simmering since 2003. When I published The Anthropic Landscape of String Theory. Look, here's the deal with the landscape. String theory predicts a huge number of possible vacuum states. It's different possible universes with different values of the cosmological constant, different particle masses, different physical constants. The number is something like 10 to the 500. That's a 1 followed by 500 zeros, an incomprehensibly large number of possible worlds. The question is, why is our universe the way it is? Why do the constants of nature have the values they have? One answer is, maybe there's a unique vacuum state, and it's ours, and we just need to find the right calculation to show that string theorists worked on finding that unique vacuum state for years, decades. They haven't found it, because it probably doesn't exist. It's another answer, and this is the one I've championed, is all those vacua are real. They're all actual universes in a vast multiverse. And we find ourselves in a universe capable of supporting life, because only in such a universe could we exist to ask the question. This is the anthropic principle, and it makes a lot of physicists deeply uncomfortable. Lee Smolin told me I'd abandon science for philosophy. It's that the landscape was unfalsifiable and therefore meaningless. And so I told him he was confusing hard to test with not science. The existence of the electron is also hard to test if you've never seen one. And the question is whether the framework makes predictions, and the landscape does, specifically about the value of the cosmological constant, which was predicted to be small and positive before it was. It's observed to be small and positive. That argument has not been resolved. I don't expect it to be resolved in my lifetime. But I think history will vindicate the anthropic approach, because I don't see what the alternative is. If the landscape is real, and I believe it is, then the universe is not fine-tuned for us. We are selected from the universe, and there's a big difference now. The firewall debate, that's the one that's affected me most personally in recent years. In 2012, a group called AMPS Almheri, Maroff, Polchinski, Sully published a paper arguing that black hole complementarity, which I had championed since 1993, was inconsistent. The argument went roughly like this. If information really escapes from a black hole, and if quantum mechanics really applies throughout, then there's a contradiction at the horizon. An infalling observer should encounter something they called a firewall. A wall of high-energy radiation instead of the smooth, featureless horizon that general relativity predicts. This was a serious challenge. I didn't dismiss it. The AMPS paper was clever and the argument was genuinely tight. My response, which came through the complexity work, was that firewalls exist in principle but are extraordinarily difficult to create in practice. To engineer a situation where a firewall forms, you'd need to perform a quantum computation of complexity that grows exponentially with the size of the black hole. The amount of computation required is so vast that it's effectively impossible for any physical system operating within the universe's timeline. This is what I call the complexity equals action argument applied to firewalls. Yes, quantum mechanics allows firewalls, but the complexity cost of creating the conditions for a firewall to form is so enormous that in practice, for almost all black holes in almost all situations, you get smooth horizons. General relativity wins, not because quantum mechanics is violated, but because the universe doesn't have time to complete the necessary computation. Is this debate over? Absolutely not. The AMPS group thinks my response doesn't fully work. I think their challenge doesn't fully work. This is what physics looks like when it's healthy. People arguing about hard things carefully with equations over years and years. I actually enjoy this. I miss having Stephen to argue with. So where are we going? What are the most important things that could happen in fundamental physics in the next decade? I'll give you my honest list as of 2026. First, quantum computers are going to get good enough to run serious quantum gravity simulations. Right now, the quantum computers we have are good enough to demonstrate proof of principle experiments like the wormhole paper we published in Nature. In 10 years, I think we'll have machines that can run the SYK model at a scale where we can actually see the emergence of bulk geometry. It's where we can watch space-time organize itself out of quantum degrees of freedom. This is going to be extraordinary. It's going to change how we think about quantum gravity, because we'll be able to experiment with it. Second, the de Sitter problem is going to force a conceptual breakthrough. It has to. We cannot go on having a beautiful theory of quantum gravity in ADs and essentially nothing in de Sitter. Our universe is de Sitter. Cosmology happens in de Sitter. It's the dark energy that's driving the accelerating expansion lives in de Sitter. If we can't do quantum gravity there, we've missed something fundamental. So I think the key is going to come from understanding the SYK model, the Sachdev-Yekitayev model, and its relationship to de Sitter space. It's the work I've been doing with Henry Lin, with Adil Rahman, exploring these connections. I think we're sniffing around the edges of something important. The de Sitter horizon behaves in some ways like a black hole. And black holes are where all my intuitions about quantum gravity live. So if I can translate the black hole lessons to de Sitter, maybe we crack it. Third, the relationship between computational complexity and gravity is going to deepen significantly. Right now, the complexity equals action conjecture is an educated guess, extremely well motivated, very consistent with everything we know, but still a conjecture. So over the next decade, I expect we'll be able to derive this relationship from more fundamental principles. And when we do, we'll have a completely new way of thinking about what space-time is. It's not a geometric arena, but a computational process. That's a paradigm shift. And I think it's coming. Fourth, and this one I have more uncertainty about. I think there's going to be something surprising from experiment. It's not necessarily from particle physics, although I'd love another discovery at the LHC, but from gravitational wave astronomy. From the observations being done by LIGO and its successors, the black holes we're observing through gravitational waves are giving us data we've never had before. I don't know if that data will connect to the theoretical questions I care about. But when you start gathering new data about black holes, the most extreme objects in the universe, you learn things you didn't expect. What I want most personally, and this is the selfish answer, is to live long enough to see a complete, consistent formulation of quantum gravity in de Sitter space. I want to see the theory that describes our universe the way AD-CFT describes anti-de Sitter universes. I want to see the 2D theory on the boundary that captures everything happening in the 4D bulk. So I want to understand what the quantum state of our cosmological horizon is. I may not make it. That's an honest thing to say at 85. But here's the thing. Even if I don't see the final answer, the conversation I've helped create, the holographic principle, ER-EPR, complexity and geometry, quantum gravity in the lab, that This conversation is going to continue. It's the students I've trained at Stanford, the papers my collaborators are working on right now, the ideas that are being debated at conferences, I'm too tired to fly to. That's all part of a single, connected project that started for me in a cluttered office at Cornell in the early 1960s when I first started asking why the world is the way it is. That project isn't finished, not even close. You know, I get asked sometimes by younger people, should I go into physics? Is there anything left to discover? Have you guys figured it all out? Have we figured it all out? Look, we don't know what 95% of the universe is made of. We call it dark matter and dark energy, which is just a fancy way of saying we don't have the faintest clue. We don't know why there's something rather than nothing, why the universe exists at all. We don't know how to reconcile our two greatest theories of nature. We don't know what happens at the center of a black hole. We don't know what time fundamentally is. We don't know whether our universe is unique or one of an incomprehensibly large number of others. If that sounds like a lot of unsolved problems, it is. And I'd say, what an extraordinary time to be alive after 60+ years of doing this. Here's what I believe most deeply. The universe is not only stranger than we think, it is stranger than we can think. At any given moment in history, every time we've broken through to a deeper level of understanding, we found something that no one could have imagined from the previous level. Quantum mechanics couldn't have been predicted from classical physics. The holographic principle couldn't have been predicted from ordinary quantum field theory. Whatever comes next, whatever the full theory of quantum gravity looks like, it's going to contain surprises that I cannot currently imagine. And that right there, that's why I still show up to my office at Stanford, still argue with my graduate students, still write papers at 85 years old, still start fights I know I might not live to see resolved because the universe is under no obligation to make sense to me, but every once in a while it does. And those moments when something that seemed impossible suddenly clicks into place, when an equation that seemed like gibberish reveals a deep truth, those moments are worth any amount of confusion. And frustration and dead ends. My father wanted me to be a plumber. He would have been pretty good at it. He had good hands. I think he's proud of me anyway. The universe still has more surprises for us. I'd bet on it. If this conversation about where physics is going interests you, and I hope it does, then watch my video on the holographic principle, where I'll go deep into the idea that reality might be fundamentally two-dimensional. That's one of the central ideas driving everything I talked about today. I'll see you there.